What's going on, everybody? We are continuing our journey through trigonometry, and you have no idea the richness of what you're about to experience over the next couple of lessons here. We're going to be learning some things that allow you to apply trigonometry to triangles that are not right triangles. We get to apply this stuff to a world that is not in which corners are not always right and things are not always straight and ideal the way that they often are on math problems. We get to apply things more to the world as it is here. I've used some of these rules on a construction site before actually, and have found that you get to cut things in custom ways that actually was to the amazement of some of my co-workers as I was doing these sorts of things. The two things we're going to be discussing are the law of sines and the law of cosines. We're going to begin today with the law of sines here. But first, we're going to start with giving ourselves some time here to focus on the present moment, to empty our mind of thoughts, to see if we can focus on our breathing for a little bit and feel that our bodies are alive, and to get our states of mind just down to the point where we are just aware of one thing only, and that is that right now you are alive. Take some time to do that. Welcome back. Well, as promised, we're going to begin here with a triangle that is not a right triangle and see what we can do with it here using the same rules of trigonometry that you've seen from the start here. Here's our opening triangle here. As you can see, by design, it is not a right triangle here, but you're going to discover some really cool things that we can do here. It's got three sides, of course, A, B, and C, and the angles A, B, and C, the same letters being opposite those that the same letters being used for an angle and a side that are opposite each other. What I'm going to do is I'm going to draw an altitude. This is called an altitude from one point to the opposite side here. I could just as easily do this from this point here to this opposite side, or from this corner here to this opposite side. But the important thing here is that it has to intersect the other side at a right angle. And look at what that does here. If we define this distance here as a height, we actually have two right triangles here to work with. One on this side and the other on this side. Excuse me. And so we're going to ask ourselves the question, what are some trigonometric relationships that we already know that involve h? Since h is a part of two right triangles here. Well, first of all, we know that the sine of A is equal to opposite over hypotenuse, so that's going to be r over c. And in the same way, we can solve for h by saying this h is equal to c sine of A. In the same way, we can also say that the sine of c is also equal to opposite over hypotenuse here. The sine of c is equal to h over a, and so we get another expression for h here. Let me get myself out of the way here. We get a second expression here for h, which is a sine of c. And it's really as simple as that here. We can make use of these two relationships here. If both of these things are equal to h, then they must be equal to each other. And so c sine of a is equal to a sine of c. And if I divide both sides by side c, little c here, I get this. And if I divide both sides by little a, side a, I get this. This is the law of sines. And again, I could just as easily draw h's from corner A, vertex A, to the opposite side A, or from vertex C to the opposite side C. And so this is actually the full law of sines here, is that if you take a look at the sine of any of the three angles here, the sine of that angle divided by the length of the opposite side is going to be equal to the same ratio for this angle and this side, and this angle here and this side. This is a relationship that's true not just for right triangles. This is true for all triangles. We can always use this, no matter what kind of triangle it is. And that's what makes this so powerful here. You're about to see just all the ways in which we can apply this. So let's actually take a look here at solving a non-right triangle here. Let's ask ourselves the question here, how much information do we need in order to be able to find out all of the angles and sides of a triangle? Do we just need to know the length of one side and one angle, or maybe two angles and nothing else, or two sides and nothing else? Let's figure out what's needed. Well, first of all, and you might recall this from some geometry here, two angles and the side in between them is actually sufficient to be able to solve the rest of what a triangle is. So if you know two angles and the side in between them, you can figure out everything else on a triangle here. And here's to demonstrate this graphically. Here's one side here, that's this length, AB, and it's this color. And in between that I have an angle that's this size and this color, that's angle A. And on the other side I have an angle here that's this size and this color, that's angle B. So I'm going to try to assemble my triangle here using these three components here. So here's side AB, here is angle A on this side here, and I've got angle B here on this side. And if that's the case, then I can fill in the rest of this here and fill in the rest of my triangle here. So two angles with the side in between them is sufficient to be able to figure out everything else on the triangle here. So we get one possible triangle from this information. Let's actually take a look at the case in which we have two angles and another side, but the side is not in between those two angles. It's in a different location on the triangle here, but we have two angles and another side that's not in between them, a non-included side, as we say. So let's come up with an example here. So here's one angle in green, in blue rather, it's this big. Another one that's red, it's this big. And lastly, we have side BC. It's not in between A and B, otherwise it would be called AB. But it's called BC here. It's black and it's this side here. So let's see if we can assemble our triangle using just these three components. Here's angle A, here's angle B, and here's angle C. Side BC rather. So you can see here that there's really only one way to put these three things together here, and that's our triangle ABC. So you might actually also remember angle, angle, side as another one of those theorems from geometry, that if you had two triangles that you could match corresponding angles, a pair of corresponding angles, another pair of corresponding angles, and a pair of corresponding sides, then you could conclude that both triangles were congruent. They were exactly the same size and shape. In the same way, you can figure out the rest of a triangle if you know two angles and one side. And there's only one possible triangle from this information. Okay, let's take a look at this one here. This is called side-side angle, and perhaps you remember this. Oh, that should say side SSA right here instead of AAS. Perhaps you remember this here from geometry. Once again, there is no side-side angle theorem when it comes to proving two triangles are congruent. And you're actually going to see why that's the case here, because you'll find that there are a bunch of different possibilities here for figuring things out here. Let's start this the same way as before here. We've got one side, AB, that's the first side. We've got a second side here in blue, BC, it's this length, that's the second side, and then we have an angle that comes after it that's in red, that's this size, that's our angle. And let's see if we can construct our triangle based on this. There's AB, there's BC, and there's the angle there. Okay, so we have one possibility here. First possibility is this. But as it turns out, there's also a second possibility here. This involves the same side here, AB, and another one that's BC here, and this angle is still the same. I can fill in the triangle this way. So in fact, you can actually see this side AB here as kind of like a doorway, that it can be either here or here. It's kind of like if you can imagine extending a line here from B that intersects perpendicular to this dotted line here. This can be on this side over here, or it can be on the exact opposite side over here. So you can kind of see two independent triangles here. Let me draw that a little better here. So if I extend an altitude here from B onto this side here, this is one possible location for AB. Here's the other possible location for AB. The side is exactly the same length as this one here, but we have, and so AB is the same, BC is the same, and angle C is the same. So we're seeing here two possibilities for triangles that have the same side lengths and an angle that's not in between the two. Side-side angle. Since there are two different possibilities, if I tell you that there are two triangles that have two corresponding sides that are the same, another pair of corresponding sides that are the same, and then an angle after that is the same, that's not enough information to be able to prove that those two triangles are congruent. There's two different possibilities here. And so you can see there are two possibilities here. So two angles with a non-included side. As it turns out, there are two possible triangles from this information, and you'll see in a minute how the law of sines deals with that. There is an instance in which you can build only a single triangle from side-side angle, and it's where this side AB here is already on that vertical altitude here that I drew, that dotted line here. And if that's the case, then there's no opposite side that it can go one to the other here. So yeah, if this intersects at a right angle here, then yeah, there's only one possibility here for the triangle from that information. But that's kind of a special case here. That doesn't happen very often. Here's a third thing that can possibly happen with side, and angle. If you watch this here, I've got this side here, I've got this side here, and I've got this angle here. And I'm asking, is there any way that I can extend this angle out here in a way that's going to intersect with this point? And the answer is no. There is no solution for this. There's no possible triangle that I can make from this because there's no way that I can connect this point here with any point that's on this angle here. There's no way that I can connect this line to anywhere on that line. So it's just kind of dangling out there in the wind. It has no place to connect to. So there are some instances in which you're given a side, you're given a side, and you're given an angle, the angle being a non-included angle, in which there is no possible triangle that can be created from that information. Let's actually take a look at side, side, side here. Oh, we have two more. Side, side, side here will be the next one. In this case, we're not given any angles, but we are given three sides. Okay, so let's take a look at this instance here. AB is this long, BC is this long, AC is this long, and they're the colors that are indicated there. So in putting those together, you can make a triangle this way, and that is enough to be able to show that we have one possible triangle that can come from that information. But there are instances similar to what we saw earlier with side-side angle in which there's no solution here. Let's take a look at this one here. I've made these sides a little bit smaller so that, as you can see here, BC is sitting here in blue, but these two sides are just dangling off their respective ends here, and they can't connect in any possible way. So these three lengths cannot form a triangle here. So if you're just given three side lengths here, it is possible that there is actually no solution that can come from that information. And this is actually something that's called the triangle inequality. I've actually seen this this thing come up on SAT tests before. It's important to know how that works here. Basically, every side has to be smaller than the other two sides added together. This side plus this side, these two things are dangling just like this. Those two sides added together, that's still smaller than the third side. That can't happen on a triangle here. So every side has to be smaller than the other two sides added together. So that's something you want to check with each of those three things here. There's actually another way of seeing that, the triangle inequality, and that is that if I draw a triangle here, A, B, C, and let's say that I give it these three values here, what's wrong with this triangle? Well, you can see here AC is too long, and so 5 and 3, those add up to just 8. So those two sides, 5 and 3, are just going to be dangling there. That's one way of seeing it. The other way of seeing it is the shortest distance between 2 points is always a straight line. So the shortest distance between A and C should be 10. And yet if I go through B, which should be a longer distance, I only go 5 plus 3, or 8. So that violates the rule that the shortest distance between 2 points should be a straight line here. So that's essentially what the triangle inequality is. It's a variant on the fact that the shortest distance between 2 points always has to be a straight line, which means that any one side of a triangle has to be smaller than the other two sides added together. And here we see an instance in which AB and AC add up to something that's still smaller than BC, and so these things are dangling. All right, lastly, let's take a look at this one here. Two sides with an angle in between them. This is side, angle, side here. So side, angle, and side here. Looks like I've already got that one there. Let's piece this together here. Here's AB, here's angle B, and here's BC. Well, it's pretty easy to see that we can construct a triangle from that pretty easily. You can see that it's almost like scissors. The first side shows you the length of one side of the scissors. The middle angle shows you how far apart the two blades on the scissors are apart from each other, and the other side describes the length of the other scissors. You can form any triangle based upon however those scissors are laid out there. So we have here a triangle that can be described with these three pieces of information. There's always only one possibility here, and so we have another instance in which there's only one possible triangle from this information. Okay, so we can summarize the last few slides here with this. Angle, side, angle, or angle, angle, side. Perhaps you remember that from geometry. Angle, side, angle. You have to go around the triangle here. If you encounter an angle first, then a side, and then an angle, or angle, angle, side. There's only one possible solution there for finding out all the other sides and all the other angles on the triangle. For side, side angle, that's where it gets pretty crazy here. The solution may be one triangle, but it could also be two triangles or no triangles at all. For side, angle, side, that's nice and neat. That's just one possible triangle. Side, 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 one possible triangle, but the sides must obey the triangle inequality. Otherwise, there's no solution whatsoever. Okay, and we're going to be solving a bunch of triangles that in which you're given different combinations of this information here. And actually, we're only going to be discussing the first two here in this lesson because this one involves the law of sines. These two instances require the law of sines. Down here, it's the next lesson, the law of cosines, which is coming soon. And in order to solve these, you really need to have the law of cosines as well. Okay, so here's an example here. Two angles, one side. This is actually angle, angle, side here. So angle, angle, side, that's why I have this sitting up here. There's only one possible solution to this. We can use the law of sines here to find a bunch of other stuff, but before we do that, we may as well find this other angle here, 102 degrees plus 29. All of the angles have to add up to 180 here, so this angle A over here has to be 49 degrees. Okay, so now we know all the angles. We just have to find the other two sides. And we can use the law of sines to do that. In this first case here, I can solve this for A. And what I've got is, I'm actually just using these two pieces here of the law of sines. A over sine of A is equal to B over sine of B, because I've got B here, it's 28. And the angle here of 29, so sine of 29. And if I solve this for A here, then all I've done here is to multiply both sides here by the sine of A. So I want you to see this here as this, where I've just multiplied both sides of the equation by sine of A. And so A is now by itself, and on this side here I've got B over sine of B times sine of A here. Now it's just a matter of plugging stuff in. The length of side B is 28, angle B is 29, angle A is 49. So 28 divided by the sine of 29 degrees multiplied by the sine of 49 degrees, that gives me 43.59 feet. That's the length of this side here. We've been able to solve these things even though this is not a right triangle here. This is so cool. So then let's do the same thing for C here. And so in this instance, I'm taking this and I'm solving for C by multiplying both sides by the sine of C here. So this is just like what I did here for finding A. And then it's just a matter of plugging everything in. And what I get here is 56.49 feet. We have solved the triangle. We found all the angles, all the sides of this triangle here. Oh, let me make so you can see that. 56.49 feet, and that's filled in here for this side. Okay, so take some time for this one here. Solve the triangle, meaning find the other angle and the other two sides. Take some time for that. Welcome back. This involved solving for one additional angle on the triangle here, that being 105 degrees, and then you were able to use the law of sines to solve for sides B and C here. So you can see the power of this really quite strongly as we're putting together, making use of this law of sines here to be able to solve for different sides and eventually angles on a triangle. All right, so here's another example here. This involves two angles with a side in between them, and we'll see just how this works here in a second here. A pole, let me get my head out of the way here, a pole tilts toward the sun at an 8-degree angle from the vertical, and it casts a 22-foot shadow. Okay, so here's a pole that's leaning towards the sun at an angle of 8 degrees, and it casts a 22-foot shadow. The angle of elevation from the tip of the shadow here to the top of the pole is 43 degrees. And so how tall is the pole? In other words, what's this length here of A? All right, so let's see if we can figure this out here. We've got 43 degrees, we've got this length here of 22 feet, and with just a little bit of math, we can find out that the angle here is just 98 degrees right here. It's a right angle here plus 8 degrees more, so a total of 98 degrees. Actually, with that in mind, we can also find out what angle B is by subtracting 98 and 43 from 180, which gives us 39 degrees left. But the real thing we want to find out here is the length of this pole here, not necessarily the height, that's a little different here, but what is the length of this pole as it is slanted? Here we can use the law of sines once again. Since we have angle A and we have angle B as well as side B here. And in doing this, we can solve this for A by multiplying both sides of the equation by sine A, and then it's just a matter of plugging things in here. 22 feet, that should say, over 39 sine of 39 degrees times the sine of 43 degrees, and that's going to give us 23.84 feet. That's the length of this pole here. All right, so here's another example here. You're being shown a tree here, a palm tree, that is leaning up, leaning at an angle of about 6 degrees here as well. And let's find the height of this tree that's casting this shadow here. You can see this angle here. It's in degrees and minutes. So do you remember how to convert degrees and minutes into decimal degrees? Take some time to remember that and to solve this problem. Welcome back. Well, the letters were a little different from A, B, C in some places here, and in addition to that, you had to find the sign values of some degrees that involve degrees and minutes here. But other than that, this was a very similar problem to the previous problem, in which we took the height here and divided it by the sine of the opposite angle here, sine of 22 degrees 50 minutes, and set that equal to the length of this side, and divided it by the sine of this angle, which we found by subtracting 22 degrees 50 minutes and 96 degrees, both from 180. And just to recall the way in which we can do the sine of 22 degrees 50 minutes here is to remember, clear this here, that there's 60 minutes in a degree. And so as we're doing this here, I'm just going to focus on the 50 minutes here. And just first, 50 divided by 60, that's equal to this. So this is the portion, the decimal portion of a single degree that 50 minutes is. And so that's 50 minutes in terms of the fraction of a degree there. I'm going to add 22 to that. All right, so this is 22 degrees 50 minutes in the form of decimal degrees. Now it's ready for me to take the sine of this, and there's the sine. So that's, as you can see, that's 0.3881 that's sitting over here. Let's do the same thing here for sine of 61 degrees 10 minutes. 10 minutes, and remembering that there's 60 minutes in a degree. So that's the decimal portion of a degree that 10 minutes is. And if I add that to 61, that is 61 degrees 10 minutes as in the form of decimal degrees. Now I can just take the sine of that, and I get this, 0.8760. So I just plug that in here. And so you can see that with that, I can get my answer here of 13.29 feet here for the height of this tree. That's not the vertical height of this tree. That's the actual slanted height of this tree. All right, in this case, we're going to start with two sides and one angle, and the angle is not in between these two sides here. This is not side angle side. This is side side angle. So this is the one that's got, a couple of different possibilities to it. And so let's see how this pans out as we're working with this particular system here. So let's first of all just use the law of sines just as we did before. 22 inches on one side divided by the sine of the opposite angle here, 42. That's going to be equal to 12 inches on this side divided by the sine of the opposite angle here. So we can use this in order to find out what B is. And so in this case we get B is equal to 21.41 degrees, and we can find out from that what C is. C is going to be 116.59 degrees. And then we can use that to find out what side C is, the only remaining side that we still haven't solved for. And when we do that, we get C is equal to 29.4 inches. So we're just using here the same techniques that we did before here in order to find angles as well as sides. All right, so use the same technique here for this particular triangle, solving for all angles, all sides. Take some time for that. Welcome back. Well, this was just really two instances of using the law of sines to solve for first an angle here, which is B, and then the second one to solve for C here, where we could actually solve the third angle here after we had our first two angles, A and B. We could subtract them from 180 to get our third angle here. So this is really just two instances in which we're using the law of sines to solve the triangle. Okay, but as I mentioned before here, there are some instances with side-side angle in which you can get some triangles, some measurements that are impossible. There are some instances in here in which we can be given some data for which it's impossible to draw a triangle here. So show that there is no triangle for which A is equal to 15, B is equal to 25, and A is equal to 85. Well, the first way in which you can demonstrate this is graphically, by drawing a picture here. So here's angle A, and angle A has to be 85 degrees here. So I have it, this is one side here, and here's the other side here, and side B here has to be 25 inches or feet or whatever it is, and then lastly this side here has to be 15. And so as you can see here, the only way in which we could get this last side here to meet up with this vertex B here is to have this angle 85 degrees a lot smaller so it could bend towards this thing a lot better. So what we're seeing here is an impossible configuration of 25, 15, and an angle of 85 degrees. Not possible. Now how does that show up with the equations? Well, if we've got the law of sines here, and by the way, you can notice that I've inverted them here. We can do that. We can take the reciprocal of both sides here. Beforehand, you were seeing this is A over sine A is equal to B over sine B. I just flip both sides. That's okay. But it allows for us to deal with these things a little bit more conveniently. As you can see here, I can plug in what the sine of, to find out what the sine of B is, I can take sine of B divided by 25, and that's going to be equal to sine of A divided by 15, A being 85 degrees. All right, so let's find out what B has to be. The sine of B has to be, it has to be 1.6603. Now let's think about that for a second. The sine of this angle has to be 1.6603. It's got to be something bigger than 1. What do we know about sine? What does it oscillate between? It oscillates between -1 and +1. Is it ever bigger than 1 or less than -1? Never. And right now we're asking this angle to have a sine that's larger than 1 here. That's impossible. So sine cannot be greater than 1. Therefore, that triangle is not possible. All right, so similarly here, show that there is no triangle for which A is equal to 4, B is equal to 14, and A is equal to 60 degrees. Do that first graphically. Try to draw that picture of A, B, and C. How do things look here? And try to scale things appropriately here. Okay, if this is 4, then 14 has got to be, something like that, a little bit more than 3 times as long. So try to draw it appropriately and try to draw an angle for A that's about 60 degrees here, like one side of a one angle of an equilateral triangle. So take some time for this. Welcome back. Well, we can clearly see that the way in which we find out that there is no possible triangle as a solution here is by taking a look at the value of sine here and noticing that it's demanding a value for the sine of an angle that is greater than 1 here. It looks like this one's even more far-fetched than the previous one here because it's asking for an angle that's not just 1 point something but 3 point something here. So it shows all the more here that this is not a possible set of measurements for any given triangle. All right, so let's take a look at the third option here. I've shown you an option in which there's only one possible triangle. I've shown you the option in which there's no possible triangle. The one that I still need to do is the option in which there are two possible triangles here. So let's take a look at this. Find two triangles for which A is equal to 12, B is equal to 31, and angle A is equal to 20.5. So let's take a look at that. Without even drawing it here, let's see how this looks here with the law of sines. And so I'm going to choose sine of B over B and sine of A over A. So notice there's no reference here to side C or angle C. So I'm going to avoid that part of the law of sines here. I'm just going to deal with B's and A's. And as it turns out, I've got everything but the value here for this angle B. So I can solve for sine of B, and I get this value here. Okay, it's not bigger than 1, so it's not impossible, so that's good. So we know that there is at least one solution here. But here we've got sine of B being equal to 0.9047, and it's true that the value of this angle here that'll give that sine is 64.78 degrees, but there's a second value for sine that also gives this value of 0.9047 degrees positive. And it's the value that comes from not quadrant 1, but quadrant 2. So if we subtract this from 180 degrees, we get this as another possible solution here. This is how you see that there are two possible solutions here. Now, you've seen us do similar things like this before, and you're probably wondering, well, how do we know that didn't show up with some of the previous ones? Well, let's actually talk about that. With this one here, as an example, let me back up even farther here and show this to you. With this one here, we had sine of B being equal to this divided by this times this. And we got 21.41 degrees as one possibility. All right, so that's quadrant 1. Quadrant 2 would have been 180 degrees minus 21.41, which would have been 158.59 degrees. Okay, so that's another value of sine that'll give us whatever these three things are divided and multiplied together here. But if angle B is 158 degrees, 158 degrees plus 42 degrees, we're already over the 180 degree maximum. So this solution is not possible here. The only possible solution was this one here from quadrant 1. We also saw that with the example problem that you did, in which you got this value here for sine, and yeah, with this value of sine here, you can get a value of B here of 12.39 degrees, or from quadrant 2, this could be 167.61 degrees. Okay, so that's a possibility. But the problem is that if angle B is that large, 167 degrees plus 31, again, we are over the 180 degree total that must exist for every triangle here. So we only have one possible solution here for B, which is how we know that we have only one possible solution for this triangle here. So now that we come to this situation here, in which we're looking at two triangles, we find that there's not just one possible solution for this, 64.78, but there's also another possible solution here, and this plus 20.5 degrees, we haven't gone over 180, so we still have some degrees left over for that third angle. This is another possible solution here. So we have two possible triangles that we can have for this. Here's the first one here, 20.5 degrees here, and here's 31, and here's 12. And here's what the other one looks like here. Just take this side and then basically swing it to the opposite side of this perpendicular here. Just basically put it here. That is the same length of this side. So this side length hasn't changed, this side length hasn't changed, this angle hasn't changed, but we get a second possibility here for a triangle. Okay, so in the same way here, find two triangles for which A is equal to 4.5, B is equal to 5, and A is equal to 58. Think about how you're going to see that through the law of sines, and then do your best to try and draw that. If you're having trouble doing some of this drawing here, just first of all draw a triangle, just any old triangle, and label things A, B, and C, and remember that the side labels are going to be the same as the angle labels here, just a lowercase letter, and they're always going to be the opposite side from this angle here. So this is angle A, so this is going to be side A. This is, be nice. This is angle B here, so this is going to be side B, and then this is angle C here, this is going to be side C. And so then start to fill things in here. This is 4.5, this is 5, and this angle here is 58 degrees. Okay, so kind of draw it freehand here first, but then start to say, okay, for 58 I got to make this a little bigger here. 4.5 and 5, that's pretty close in size here, so how can I make this work? So take some time for that. Welcome back. Well, probably the most challenging part of this problem is doing the drawing. I know that that's the case for me, and you probably saw that pretty strongly as you tried to watch me draw through this. Not a very easy thing to do there, but as you can see two different possibilities here for B. And in this case, I actually didn't follow my own advice here and stuck B on the bottom instead of the top here. But you can see here that the angles here, angle A is 58 degrees, and angle B here can have two different values of 70.43 or 109.57 angles. So you can kind of see just those two possible solutions there. Okay, so here's a bonus that comes from learning the law of sines, rather. If you recall, when we were learning how to find the area of a triangle, it was always 1/2 base times height. So if you're given the three sides of a triangle, you always had to have this annoying extra length here from the top of the triangle to the bottom here, the perpendicular height from the base of the triangle, in order to be able to solve for the area of the triangle. Not the case anymore. We don't need to have that any longer here. So if we start off with our original equation here, 1/2 base times height, let's assume that C here is the base and H is the height. We could just plug that in for base and height. And then how can we express H in terms of some of the other sides, as well as some trig functions of some other angles here? And we can express H as being the sine of A times B here. Since the sine of A is equal to H over B, and that means that H is equal to B times the sine of A. And that's what we're doing here in substituting this in for H. We have B times sine of A placed in there. So now, notice, we can find the area of this triangle without using H. We use C and B, these two sides, times the sine of A. And there's the two formulas there that I was talking about. So we have here this formula, area is equal to 1/2 BC times the sine of A. Now that just came from drawing my altitude this way, the height this way. Could have just as easily taken the same triangle, turned it on another side, called that the base, drew another perpendicular height to another side here, and gotten a different formula. I could have also turn the triangle over on its third side, called that the base, and drew another height that way here. So what you're seeing here is not the only formula here for area. There is actually three possible formulas here. 1/2 BC sine of A, 1/2 AC sine of B, or 1/2 AB sine of C. So basically the only rule here is that the angle has to be whatever letter is not represented by these two other sides here. So BC sine of A, AC sine of B, or AB sine of C. Another way of seeing it is it's two sides multiplied together times the sine of the angle in between them. AC sine of B, AB sine of C, BC sine of A. So it's two sides multiplied together times the sine of the angle in between those two sides. Now, if you see here, if I make it so this triangle is a right triangle, then here side B in this case is exactly the same as side H, and so the sine of A in this case is equal to 1, which means that our new formula here just becomes 1/2 base times height. So when this becomes a right triangle here, it actually becomes the exact same formula as 1/2 base times height that we had before here. So you can see that that has a connection to our previous formula. Finding the area of a triangular lot here. So find the area of a triangular lot having two sides of lengths 90 meters and 52 meters and an included angle, that's the angle in between them, of 102 degrees. Okay, so this side has to be 52 meters, this side has to be 90 meters, the angle in between them is 102 degrees here. So what's the formula that we're going to use here? Probably 1/2 AB sine of C. 1/2 AB sine of C. We just plug things in. 1/2 90 times 52 times the sine of 102. This lot here is about, oh, that should say 2,229 square meters in size. And it just came from using one of these formulas here. Okay, with that in mind, do this very similar problem here. Find the area of a triangular lot having two sides of lengths 24 inches and 18 inches and an included angle of 80 degrees there. Take some time for that. Welcome back. Well, this problem was very similar to the one that we did previously here. We're just working here in inches instead of meters, much to my mistake there. You can see there that should be square inches, not meters. But we just took 1/2 A times B times sine of C, plugged things in, and got a value of about 213 square inches. Okay, so here's an example of an application here. The course for a boat race starts at point A and proceeds in the direction south 52 degrees west to point B, then in the direction south 40 degrees east to point C, and then finally back to point A as shown in the figure. Point C lies 8 kilometers directly south of point A. So approximate the total distance of the race course here. So we've got a triangle here to work with, and as you can see here, I've already done some of the work here. I should have put these in animations here. But here, this 40 degrees and this 88 degrees wasn't actually given in the problem here. But you can see how we can solve this here. This line is parallel to this line here. It's cut by a transversal, and so alternating interior angles here should be the same size. So if this is 40 degrees here, then this should be 40 degrees here. Then of course we can find out what this angle is by subtracting this and this from 180 degrees leaving behind just 88 degrees for this angle. Okay, then we've got everything that we need here in order to be able to solve for A, that's this side here, and C, which is this side here. We already have the length of this side here, which is 8 kilometers. We just have to find these other two here. So let's first of all work on A, and we'll make use of just these two portions of it here. Solve for A, and we get 6.308 kilometers. In the same way, we can make use of these latter two portions here, and we can solve for C and get 5.145 kilometers. Now it's asking here specifically for the total distance of the race course, so that's going to be A plus B plus C, so it's going to be this plus 8 kilometers plus this for a total of 19.453 kilometers here. So this part was easy. It was really just the part of making use of the law of sines here to find out what these other two sides are. And we had to do some geometry stuff here in order to figure out what some of these angles were to help with that. So go ahead and do this problem here as well. On a small lake, you swim from point A to point B at a bearing of north 28 degrees east, then to point C at a bearing of north 58 degrees west, and then finally back to point A as shown in the figure. And point A lies exactly 800 meters south of point C, and approximate the total distance that you swim here. So take some time for that. Welcome back. Well, this problem was very similar to the one previous to it, in which you are taking a look at, you're given one angle and you're able to find the second and third angles through doing some geometry here on parallel lines. 58 degrees and 94 degrees allows you to use the law of sines rather to solve for A and C, and you get the total distance that way. All right, so let's summarize this from the start here. We've been, first of all, finding out how to use the law of sines to find unknown sides and angles of triangles. We've been doing that with triangles that, for the first time, don't have to be right triangles. Second thing, using the law of sines to find which combinations of sides and angles have no solutions, just one solution or two solutions that are possible. Remember, that value of that sign tends to determine what the outcome is for that. Finding the area of a triangle that's not a right triangle, and without knowing what that height is from the inside. And lastly, using this to solve some real-world problems. And there are so many real-world problems that this opens you up to, because it allows you to deal with the world in which you don't have to have a right triangle. You can have something that is just any triangle whatsoever here. Isn't it cool that we can now use trigonometry to work with any triangle, angles and sides, regardless of whether or not this is a right triangle? I told you this stuff was cool. So I'll see you next time, and hopefully that will be enough to get you through the next assignment here, and I'll see you in class.